Continue talking about strings today. And actually, we're going to focus on the last two problems that we saw in the last session. So problem 4 and problem 5. Now, we don't have a set of strings anymore. We just have one string S. And in problem 5, we get a bunch of queries every time I give you some string T, and you have to say, is T a substring of S? And if T is a substring of S, I want you to tell me how many times it appears in S, and I also want to know where it appears. So what are the indices in S from which if I start reading, I can read a copy of T? Okay. Now, in the last session, we already saw tries, and I just drew something else. So here's a try for these words. And as before, we talked about this, that we're going to have an end of word character. And I'm going to assume that my end of word character is smaller in the alphabetical order than all of my other characters. Okay, so if I have these words, this is actually how the try looks like. And we talked about how to create a try. We talked about how to search in a try. It's actually very simple, right? You always start at the root, and you just keep walking down the try, taking one edge at a time, and every edge corresponds to exactly one letter of your string. So for example, here, if I'm searching, for example, let's say for shelf, I would just start at the top. I'll start here. I read S, H, E, L, and F. And of course, I'm also going to read the end of word character. And because I could find this word, I know that this word exists in my set. Whereas if I was searching, for example, for, I don't know, let's say SF, I read S and then there is no F to read. So I know that that word doesn't exist. Similarly, if I were to search for, let's say, shell, I would read S, H, E, L, L. But now I need to read an end of word character, and there is no end of word character at this point. So I know that shell doesn't exist either. Okay. So we saw that if we have a string of length k, searching for it takes OK time, adding it takes OK time, removing actually also takes OK time. You can just search for it. So let's say I want to remove some string. Let's say I want to remove shellfish here. I can just search for it first. I start at the top. I go through this path. I find shellfish. Now, I remove everything in this path that is not used anywhere else. Okay, so I would remove the leaf. And then I go to the parent. If this parent doesn't have any other children, I would remove that too, and so on. So I would remove everything up until here, but then this node remains there because it has other children. So removing can also be done in OK. Now, we talked towards the end of the last session about the fact that the try usually has way too many vertices. So I would like to have fewer vertices. And we had this idea of compressing a try. And the idea of compression was that whenever I have a path, whenever I have something like this, basically a bunch of nodes that each have only one child, right? I don't need to keep all of this. I can just create one edge instead. I can merge this whole path into one edge. And I can change the label of that edge to be just the string, in this case, HKUST. And okay. So that's what we called a compressed try. And here's the compressed try for the same words as the previous try. Now, the really nice property in a compressed try is that every vertex is either a leaf or it has at least two children. Because that was part of our definition of compression. If it had only one child, I would just compress it and make it the same as its child, right? I would merge it with its child. So based on this, we proved in the last session that the number of internal nodes, the number of blue nodes here, is less than the number of leaves. So if I have n leaves, I have at most n minus 1 internal. Okay. And we also talked about the fact that the number of leaves is exactly equal to the number of strings that I have in my set, because there is a one-to-one correspondence between the strings and the leaves. So this means that this is much smaller than a trie if you only look at the number of vertices. It actually has only O(n) vertices, whereas a trie could have O(n) times k, or n squared if k and n are the same, right? But of course, we talked about the fact that this doesn't help us too much with memory usage, because now the labels themselves can be really long. So I can have a label that is not just one character, but a string now, and maybe this label is n characters or k characters long. So my total space usage doesn't change by more than a constant factor. Okay. But the thing I want you to realize here is that instead of working with just a normal trie, I can always work with a compressed trie. Right? So I can always just insert and search and delete and do all of the things that I was doing on the compressed version already. Okay. So I found some nice website here. Yeah. This shows how a compressed trie works. Let's add these words and let's ask it to create a compressed trie. Unfortunately, this website doesn't support this particular sign, so I'm just going to use X as my end character. So I insert cell X, and as you see, because it's a compressed trie, it just inserts it, right? Now I'm going to insert self. What happens if I want to insert self? Well, I'm going to start here, and then now in this case, it has written the label on the vertex, but in our case, we write the label, of course, on the edge. So I'm going to look at this edge, and I'm going to try to match the string that I have with this edge. And I'm going to see that the first 3 characters match, right? But because only 3 characters match, I'm going to basically break this edge down. I'm going to add an internal vertex such that I keep the first 3 characters, and then I create 2 different children after that. So if I insert self here, this is what's happening. So this edge is labeled cell, and then this edge is F. Oh, I forgot to put the X at the end. Let me go back. Oh, how does this work? Okay. Let's do this again. So I'm inserting cell, and then I'm inserting self. I want to have an X at the end. And so the prefix that was shared was only created once, and then it has 2 children. On one side, I have fx. On the other side, I have lx. Okay. And then I can continue this. So if I want to insert selfish, for example, I see that in this edge, I have SEL, which are the first 3 letters. So I can traverse this edge and come here. And then on this edge, I see that I have F. So I can traverse half of this edge, because then I have an X on the edge, but here I have an I. So again, I have to add an internal vertex between this vertex and this vertex. And you will see that that's exactly what's going to happen here. Okay. So the fx vertex broke down. I have f here, x here, and then x on the other side. And basically, you can do searching, you can do removal, everything. It's basically the same as before. It's just that whenever you're passing through an edge, instead of passing through it in just one step, you might pass through half of it or some portion of it, right? So this is pretty easy to implement. We can just use the compressed versions from now on. But this is not the main topic for today. So we've already seen how to use tries and compressed tries to solve 3 other problems. But today I want to focus on problem 4 and especially on problem 5, which is that I have just one important string S. And then I want to answer a bunch of queries that ask me, is this given T a substring of your string S or not? Okay. So why am I talking about tries and compressed tries if I have only one string? Because the idea is that I can look at all of the suffix all of the suffixes of my string, and I can create a trie out of them. This is called a suffix trie. So let's say that my string S is this. Let's say my string S is bananas na, and the X is just end of string symbol in this case. Okay. Why am I using X? Because that tool doesn't support Sharp. And why am I using bananas now? Because there is a YouTube video that uses this. I can give it to you to watch later. Okay. So I create this suffix trie, and this is my suffix trie. It looks nice, but it's kind of big. So if the length of my string is n, this might have n squared vertices. So I'm already spending O(n) squared just to create my suffix trie. Okay. So let's say this is my pre-processing time, O(n) squared pre-processing, creating this suffix trie. And now let's say that someone gives me a string t and asks me, is t a substring of S? How can I answer that? Well, the intuition here is actually very simple. Suppose that I have my string S. Let's say this is my string S. This is S. And let's say that T is a substring. So this is T. Okay. If T is a substring, then T is a prefix of a suffix. So there is some suffix of S, particularly this suffix, such that T is a prefix of this suffix. Right? And you can check that this is like an if and only if condition. So T is a substring if and only if it's a prefix of a suffix. Okay. But remember, the other name for tries was prefix trees, because I could easily answer if a given string is a prefix of one of my strings in my trie. I would just start at the top of the trie, try to go through that string. So for example, if I want SHE, I would just start here, go down SHE, and if I don't fall off, if I always have the edges that I was looking for, that means this is the prefix of one of my strings, right? Now, the only difference here is that my strings are not arbitrary strings. They're just suffixes of my original string S. So I can easily ask this trie whether T is a prefix of one of these strings, which would mean that T is a prefix of a suffix of S, which would mean that T is a substring of S. Okay. So I'm doing O(n) squared pre-processing, and remember that n was the length of S. Now, when someone asks for substr T, basically asks me whether T is a substring, how much time am I going to spend to answer this? Well, just the length of T, right? Because I'm just starting at the top of my suffix trie, going down by T steps. So this is great. And I don't like the fact that my pre-processing is taking so long, but at least I'm answering the queries optimally. There's no way I can answer my queries asymptotically faster than this, because at the very least, again, I have to read my string T, right? And if I just read it, it's going to take OT. Okay, great. So I have an optimal way of answering the queries, no matter how many queries I have, as long as you give me O(n) squared time in pre-processing. So the most important thing in this session is to reduce this O(n) squared while keeping this one optimal. Okay, first, we're going to use this idea. Let's say that instead of having a trie of suffixes, I have a compressed trie of suffixes, a compressed suffix trie. Okay, so I can just take all of these suffixes and I can put them in a compressed trie. And let me just refresh this. How can I copy? Okay, so I'm just going to insert these. Oh, the speed is not too good. I'm taking all of my suffixes and I'm inserting them in a trie, but it's a compressed trie. To do this one by one. Thank God I don't have to draw it myself. Okay. So this is my compressed suffix drive. Now I had it here too. So the thing about compressed drives, and again, this tool puts the labels in the vertices, but for this course, imagine that the labels are on the edges. So just imagine that this label is actually on the edge that is going to this vertex. Okay. So we know that if we have a compressed trie, and if we have n vertices in there, if I have n strings in there, then I have O(n) vertices. I just proved this, right? Now, if I have a string of length n, how many suffixes does it have? Well, n, right? So the size of this trie in terms of number of vertices is actually very good. It's O(n). My only problem is that these labels, they're nasty. They're taking a lot of space. That's why I have O(n) squared. Okay. So I'm going to go from a compressed suffix trie to something that I call a suffix tree. Now, what is a suffix tree? To show you that, I have to just copy this. Okay. Let's put it here. And let me also copy my original string. Okay. So here's the thing. Look at my string. This is my string S. And of course, I also have some indices. So I can start indexing it from 0 or 1, whichever you like. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is 10. Okay. Now, my problem is with the labels. But if you look at the labels, all of these labels are substrings of S. Right? That's just in the nature of how we are creating them, because all these labels are actually substrings of strings that I put into my trie. But the strings that I put into my trie were suffixes of S, so they were themselves substrings of S. So every label here is a substring of S. So instead of saving these labels, I can just save S, and then I can save indices saying which part of S this label corresponds to. Okay, so for example, look at this one. Bananas na X, so that's the entirety of S. Okay, it's all of S. So this is S from index 1 to index 10. Instead of saving this whole thing, on this edge, I'm just going to save the start index and the end index. I'm just going to save two numbers, 1 and 10. Okay. Now, this is as good as saving the label itself, because I know what my string S is, and all I'm saying here is that this label is the substring from index 1 to 10 of S. So any operation that I was doing on my trie, I can still do it in the same runtime, because I can still access the labels of my trie, right? And I can do the same thing. So for example, if this na, I don't know which na it is, but it doesn't really matter. Let's say it's this one from 3 to 4, right? So I can just say that here on this edge, I just save the numbers 3 and 4. I have a snacks here, which is from 7 to 10. So on this edge, I would just save the numbers 7 and 10, and so on. On every edge, I'm just saving two numbers, the start point and the end. And that's it. This is what I call a suffix tree. So it's just a compressed suffix trie with the extra smartness that I'm not going to save all of the labels. Instead, I'm just going to save, let's say, pointers to the labels. I'm just going to say, this is a label that starts at this index of S and ends at this index. Okay. Now you can easily see that, again, I can do all the operations that I was doing before, because it doesn't matter how I was saving my label. The only thing that mattered to me was that I could access my label, and I can access it now. So I can still answer each one of these queries in the same runtime, in OT. But now the size of my data structure has really reduced. Previously, the size of my data structure, the amount of space that I needed for my data structure, was n squared. But now I only need on space. Because remember, the number of vertices in a compressed trie is on. And now for every vertex, or actually for every edge, I'm just saving two numbers. So the total space that I'm using is on. Okay, so on space in pre-processing. But this doesn't mean that I could actually create this tree in on. My pre-processing is still taking on squared time. The space has reduced, but the time is the same, right? I'm just using the same algorithm. I'm inserting n different strings of lengths 1 to n into a trie, and it's going to take on squared. So assuming that I can find a better way to solve this, assuming that I can somehow compute my suffix tree faster, I would then be able to answer each query in optimum time, which is exactly what I want. But before going there, I want to show you how I can do some other operations using this suffix tree. So we've seen that if I have a suffix tree, if someone gives me the suffix tree, then I can answer these in OT. Okay. And of course, the same thing if I'm given a suffix trie. For that, I can also answer these queries in OT. But of course, the difference was that the suffix trie needed quadratic space. A suffix tree only needs linear space. We're going to see how to find it in linear time later in this session. But now, let me see, can I answer these other queries? So suppose that I have magically given you the suffix tree, and now I'm asking you, how many times does the string t appear as a substring of S? Or where does t appear in S? To answer these questions, let's just go back to the suffix trie. So this is generally how we're designing algorithms here. We first say how we do it on the suffix trie. Then we say what should we change in our algorithm if we compress the trie. Then we say what should we change if we have a suffix tree. Okay. So that makes it really easy to design algorithms. So suppose I have a string t, and I want to ask how many of the suffixes have this string t as a prefix. Basically, this is the same as asking how many times does t appear in S. Okay, every suffix corresponds to one of the leaves in here. So basically, when I find a string, for example, let's say I ask you how many substrings contain an. I can just search for an, and this is like the node that corresponds to an. And basically the question is, how many leaves are there in the subtree of this node? Right? Because if I look at an, which is this node, all the strings that lead to a leaf in this subtree are exactly the suffixes that have this an as their prefix. So in this case, there are two. So an appears twice, right? I can see that an appears here and here. It appears twice. Now, what if I want, let's say, na? I can start here, and I can take the edge for n and the edge for a. So I get here. Now the question is, how many leaves do I have in this subtree? And in this case, I have 3 leaves. So the answer is just 3. And you can see that I can actually find 3 NAs as well. So I have one here, and one here. Okay. Okay, let's do just one more. Suppose that my T is ANA. So I start from here to ANA, and then I ask how many leaves do I have? And in this case, I have 2 leaves. So ANA should appear twice in the string S. And it does appear twice. This is the first time, this is the second time. So this counts as 2 different appearances, even though they have some precision. Okay. So now I know that when someone asks me how many times the string T appears in the string S, I just have to look at this try, find T, and then I have to answer how many leaves are there in the subtree of T. But how would I answer that fast? Well, in this try, you can just save the subtree sizes. Right? So as you're doing all the other operations, just keep track of the number of leaves in the subtree of each node. Not the subtree size really, because I'm only counting the leaves, but just keep track of that. And then when you want to answer how many leaves are descendants of T, you just basically have to search for T. So you're going to answer that in the same runtime as before, which is O lengths of T. Now, the other question was, where are these? Like, give me the indices, give me the exact indices. Okay. That's also not a big problem, right? Because at these leaves, instead of just saving an X, I could save the indices. And then at every node, let's say I don't care about space at this point. So at every node, I can also save a list of indices that appear in the leaves of its subtree. And then when I get to that node, I just print those. Okay. So again, my runtime is optimal because in this case, my runtime would be to first search for T. So that's going to take OT. And then I already have the answer pre-computed and I'm just going to print the answer. So my total runtime is lengths of T plus lengths of the answer. But again, that's optimal because you need lengths of T to at least read the query, and then you need lengths of the answer to write it, right? So you cannot do it any faster than that. Great. So this is how we could do it in a suffix try. But let's say I have a compressed suffix try. Again, all of the same ideas work. It's just that it's a little bit harder to implement. You just have to do the same thing. Just remember which indices these leaves correspond to, and also remember how many leaves are in the subtree of every node. Okay. Now, if we go to a suffix tree instead, a suffix tree is basically the same as a compressed suffix try. The only difference is that these labels are not saved separately. They're just pointers to somewhere in the string S. So any algorithm that I'm running on the compressed suffix try, I can also run it on suffix tree. Okay. So going back to here, actually, this one, how many times, can also be answered again in O of T. And where they appear can be answered in O of T plus the number of appearances. Let's call that A. Okay. Great. What about problem 4? I've given you a string S, and I'm asking you what is the longest repeated substring of S. Okay. We said that a string T is repeated if when we find it in this try, its subtree has at least 2 leaves, right? But I want the longest string that is repeated. So what is the lowest node here that has at least 2 leaves in its subtree? And that's also pretty easy to compute, right? So again, you just keep track of how many leaves you have in the subtree of every node. And among all the nodes that have a subtree size, a subtree leaf size of 2 or larger, you just find the one that has the most depths. And we know how to keep track of depths as well. So just add those things. This is actually very similar to the lecture on DFS now I'm realizing. Okay. And also, it doesn't matter if I say what is the longest substring that repeats 2 times or R times. It's just that if I give you an R, you want to find the lowest node such that its subtree has more than R leaves, R or more leaves, right? And again, you can just answer that very easily. So as long as you can create your suffix tree, you can basically answer all of these with some pre-computations when you're doing the suffix tree. You can answer all of these in O1 in problem 4. Okay, so this is O1 if I am given a suffix tree or a suffix trie or a compressed suffix trie, it doesn't matter. If I have any of these, I can answer this. Okay. How do we actually build this thing now? We know that it's very useful. And we know that it's not too big. I know that the size of my suffix tree is ON. But right now, all the algorithms that I have for creating it take n squared time. So any ideas? Maybe you can just solve it in a moment. Okay, so there is this famous algorithm. It's called Ukkonen's algorithm. And we're going to talk about it. This is probably the most complicated algorithm in this course, but the ideas are actually very simple. So just try to keep up with the example and you'll be fine. Okay, so Ukkonen's algorithm. So the idea in Ukkonen's algorithm is that we're just going to create a compressed suffix trie. Okay, so if I'm given, for example, this string, I'm just going to try to create this. With the extra assumption that instead of actually saving the leaves at every time, like every time at every step of the algorithm, I'm just going to save these leaves, these labels implicitly. I'm just going to keep the starting point and the end point. Okay. But it's actually a little bit more complicated than that, because I cannot just insert n suffixes, because that would take n squared time. And I want to create that whole suffix tree in ON. So instead, I'm going to start from the beginning of my string, and I'm going to do what's called an online algorithm, which means that I'm adding my letters one by one. Okay. So let me just copy the string that I have here. Bananas na. Okay. And let's say that again, I have the indices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so I'm going to add the letters one by one. So first, I'm just going to add the letter B, which means that I'm assuming that my string is only B. So if my string is only B, what does the suffix tree of that one letter look like? Well, B has only one suffix, that's B itself. So I can just have something like this. I can have one node and I can have one edge labeled B. And I'm going to show my leaves as squares. It doesn't really matter, but I want you to know which ones are internal nodes and which ones are leaves. So in this case, this is an internal node. Now, this is kind of violating our rule that all the internal nodes should have at least 2 children. But this is the only case where that's violated, because I have only one leaf. I cannot have 2 children for the internal node. Okay, so I consider this a valid suffix tree, let's say. Okay, and also, when I'm explaining the algorithm to you, I'm just writing the labels here, but I want you to constantly remember that the labels are not actually saved. What's saved here is just the indices. So I don't actually save B in my algorithm. What I'm saving in my algorithm is 1, 1. Okay, so from index 1 to index 1. Generally speaking, I will just have a counter, let's call it I, and it's like in the I step of my algorithm, I'm processing the first I letters. So initially, my I is 1. And again, this is a very weird thing. I don't really save 1, 1, I save 1 I here. So my algorithm is not going to just save a number. In some cases, it's just going to save a variable. So it's a symbolic algorithm in some sense, half symbolic. Because later on, when I increase the I want this to increase automatically. Okay, so again, this B that I'm writing here, that's what we think about when we are thinking about the algorithm mathematically. But 1 I is what the algorithm is actually saving. Okay, so the first letter was easy. Let's say now I go to the second letter. So my I is now 2. Now, what are my suffixes? My suffixes are 2 now. There is one suffix that starts at index 2, and there is one suffix that starts at index 1. But here's the beauty of the algorithm, because I said that this is from 1 to I. Now this has automatically became BA, right? Because now my I is 2. Right? So I have that suffix. I have the suffix BA. I just need to add the second suffix A. And in this case, BA and A start with different letters. So that's easy. If I have this, again, think of this as a compressed trie. I'm just going to add A like this. Right? But again, what is the algorithm saving? The algorithm is just saving the indices corresponding to this. So it's actually saving 2I. Okay. It's not complicated yet. It will get much more complicated really soon. So I now have my answer if I only had my first 2 letters. Let's go ahead and let's increase our I, and let's add the third letter. Again, as soon as I do this, my first 2 suffixes are fine, because this one was from 1 to I and this one was from 2 to I, and now I've increased my I. So this one corresponds to BAN now, and this one corresponds to AN. Right? And again, I'm not saving these strings in my algorithm. All I had saved in my algorithm was just 2 and I, and now I increased I. So I didn't have to even change these labels. It's just that their meaning changed. Right? Now I have to add this new thing that I have, this new suffix that I have, which is just N. Again, I get lucky because the first character of N does not appear in any of these labels, at the beginning of any of these labels. So I can just add N. So I'll add just another child here. And the label here is from 3 to I. And basically, again, the string that we're thinking of is N. Now, another thing that sometimes people do in their implementation is that at every leaf, you just save the label of the starting index of the suffix that corresponds to that leaf. You can also do that. I don't really care about it, but let's just do it. So let's say this one is 1, this is 2, this is 3. Right? So this node corresponds to the suffix that starts at index 3. Of course, for suffixes, I don't need the end index because it's just the end of the string. Okay. The interesting part is when I increase my I again, and now I want to add the next letter, which is an A. Now, when I want to add A, the problem is that I already have an edge going out of my root whose label starts with A. Right? So what can I do? At this point, I don't know what the rest of my string is going to be. So at this point, I have read only the first 4 characters. So it might be that if I continue, I see an n later on, and so I wouldn't need to break this edge into two. But it also might be that the next character is something else. Maybe the next character is, I don't know, x, let's say. And then in that case, I would have to break this edge into two edges. I would basically have to have an A edge followed by an N edge, and then there should be like an X edge going out, right? So at this point, I don't know what I have to do. It depends on the characters that I have not yet read. So all I'm going to do is to remember that I have to come back to this. So at this point, I'm not going to change my tree. I'm just going to say, remember that you haven't added this. Now, let me use the same terminology as here. So I'm going to keep a variable called remainder. And this remainder is basically the number of suffixes that I had to add, but I haven't added yet. Okay, so the remainder was 0 until this point, but now I'm going to make the remainder 1. So all this means is that since my I is 4, I have read the first 4 characters. I have created a tree for the first 3 characters, and the last character remains. Okay, so sorry, I have created a tree for the suffixes corresponding to the first 3 characters, and the suffix corresponding to the last character remains. Other than this, I'm also going to remember something else. I'm going to remember that I have read the first character A of this string. So I'm going to put a pointer here saying, remember, I'm here. Okay. Now, what does this pointer look like? Well, this is where what we call our active location. So it consists of 3 parts. Which node am I in? Which edge of that node? And where in that edge? Okay. So basically, I'm just putting a line here. I'm saying, imagine that I'm between A and N. Okay. But how can I really code that? I can say that I am at this node, and then this edge of the node, the edge AN, and then I have gone 1 letter in. Okay. So that's all these things are: active node, active edge, active length. It just tells you where you are. So yeah, at this point, I would just say, I'm going here, and that's my location. I'm happy with this. I'm going to increase my I. So I'm going to increase my I to 5. And again, you see, as soon as I increase my I to 5, because this one was 1I, the string here is actually increasing. This is becoming BANA. Oh, I forgot to increase it before. BANAN. And this is 2 to I, so it's ANAN. And this is 3 to I, so it's NAN. Okay. So now that I have increased my I to 5, this is what I have. And again, I have this pointer that tells me where I am. And the letter I just read was N. And I'm lucky because in this label here, the next letter is also N. So I can match this. I can just keep going forward. Okay. So again, I take this. Let's say, let me write it here. At this point, my I became 5. And then I just go 1 letter forward. So I had ANAN, and now I say I'm here. Okay. Now, what happens to my remainder? My remainder was 1, but now my remainder is 2, because I haven't added my last 2 suffixes. Okay. I continue like this. I increase my I, so I go to the next character, and going to the next character automatically adds it to all of these labels. Okay. And again, I check, and I see that I'm lucky. I have an A here, and I also have an A here. So this matched again. So I can just move my pointer forward. So I had an A here. I just put my pointer here. And now my remainder is 3. I haven't added my last 3 suffixes yet. So as long as there is a match, I keep matching, and I just keep moving this pointer forward. And I mean, if I match all of this edge, that's fine. I'll just continue going down my track. Okay. As long as there is a match, I'm going to be lazy and not add the new suffixes. Okay. Finally, at 7, when my I goes forward and it becomes 7, what's happening here? I have an S. So the first thing is that all of these labels are implicitly updated. So all of these labels are S, S, S. Okay. And now the S actually does not match with the next letter here, which is an N. So at this point, I know that I have to break this edge. And I have to break it into an edge that has ANA, ANA, and then followed by an edge that has NAS. Right? Because there was something from before that had this ananas here, and the ANA part has been matched, but now after the ANA part, I have an S. So I need a child after ANA that is S, and I need another child that is NAS. Okay. So let me just copy this. And remember that at this point, my I is 7. So I had this. I'm going to remove it. I'm going to add a new internal node. And this internal node is going to have 2 children. One child, which is 2, corresponds to what this edge was before. And the other child, which is just S, is going to be new. Okay, so I put this here. And what should I put in this child? What is the index that I have to put here? It's my I, it's 7 basically. Right? No, it's not 7. So, oh, we have to be careful about this. So here, when I was going through this edge, I was seeing 2 to I, right? But then, based on my remainder, I know how many of the things I hadn't matched, how many of the suffixes I haven't added to my suffix tree yet. So my remainder is 3. So I know that since index 4, I haven't added any suffixes. Okay, so this suffix that I'm adding right now is the suffix that started at index 4. It's ANAS. Yes, it's ANAS. Right? So actually, I have to put 4 here. But now, what happens to my remainder? I have added all the suffixes corresponding to indices from 1 to 4. So I haven't yet added 5, 6, and 7. So my remainder is still 3. Right? Okay. Actually, my remainder first increased to 4 when I went to 7, and then now it's again 3. So that's my remainder. But where is my location? Where should I continue matching after this? So you see, I had matched up until this point, Anna, and then I read the S. So this gave me this 4. Right? But now that I have this 4 here, let's look at, for example, the next suffix, the suffix that starts at 5. And remember, I have only read my first 7 letters at this point. So the suffix that starts at 5 is NAS. Okay. I want to continue matching on that suffix. So I want to add NAS here. If I want to add NAS, where should I add it? Well, I have to come here, right? I have to go after this NA. Right? So my new location would be here. But how am I finding this new location? How did I know that I could just come here? I don't want to go all the way back and start matching again from index 5, because if I do that, then I would get a quadratic time algorithm, right? So after I do this operation, after I took this edge and basically cut it down and added this middle vertex here, I want to be able to easily jump to the next place. I don't want to waste any time in this jump. Now, here's the thing. I can use my remainder and my current location to find my next location. So before I did this, what did I know? I knew that I haven't matched 4, 5, 6, and 7. So my remainder was actually 4 at that point because I hadn't matched 4, 5, 6, and 7, right? Now I have matched, or I have added the suffix that started at index 4, right? So now I know that this one, the Anas, is actually in the tree. But now I want the suffix that starts at index 5. Okay. But how would I find that easily? You see here, I had already matched 3 letters. If I have matched 3 letters here already, these were 3 letters starting from which index? From index 2. So matching 3 letters starting from index 2 is the same as matching 2 letters starting from index 3. If you start at index 2 and go forward by 3 letters, you end up at the same place than if you start at index 3 and go forward by 2. So, and I had this one here. This is the suffix that starts at index 3, right? So I have to take the suffix that starts at index 3 and go forward in it by 2 steps. So basically, the only thing that is changing here is that instead of looking at the suffix that starts at index 2, I will have to go to the edge that corresponded to the suffix that started at index 3, which I already know where it is. And then instead of having a match of length 3, now I have a match of length 2. So that's why from here, I'm ending up here. I'm going to this one, and then I have already matched NA. So this is the whole genius of this algorithm. I don't have to go back and rematch all these suffixes. Because I had a match of length 3 starting from this index, I know that, sorry, because I had a match of, length 3 starting from this index, I know that I have a match of length 2 starting from this index. Okay, my I is still 7. I have read only 7 letters. I'm here. I'm reading the 7th letter, which is S. So I want to add an S here, and again, it does not match. So I have to now take this one, and I have to break it into 2 edges. Okay. So I'm just going to copy this now. Okay, so the na part is going to stay. And remember what the indices were at this point. So na is index 3 to 4. Right, so this is what the algorithm is actually saving. It's not saving any of the labels, it's just saving the indices of the labels. And then I will have an internal node here. So one internal node. And one of its children is the rest of this string, which is nas. And it's basically 3. And what is the label that is saved for this? What is the actual thing that the algorithm saves? Basically, the starting index and the end index. So the starting index here is 5, because the starting index here was 3, and we are taking this part, which is like 2 letters forward. And the end letter is I. Okay. And of course, the letter I was adding was S. So I'm going to have a child here labeled S. Okay, what is the index that I should put here? Again, I can compute it based on all the things that I have until this point, but you would also realize that it's in order, so it's just 5. Right. How else could I compute this? Well, I could say that I have this thing, which was the thing starting at 3, and the first 2 letters matched. And I'm at index 7 right now. If the first 2 letters matched, everything from index 5 forward has been matched. So that means it starts from 5. And now at letter 7, I've seen an S instead of the N that I had here. So this S corresponds to the suffix that starts at index 5. Again, kind of confusing, but honestly makes perfect sense. Okay. So here's the thing. I'm still at I equal to 7. This step has not ended yet. I have to continue. But here's another weird thing in this algorithm. When I was 7, when I was adding the 7th letter, I have already added 2 different internal nodes right now. Okay. Because I have added 2 different internal nodes, I'm going to also add a different kind of edge between these 2 nodes, just to remember that they were added for the same value of I. And I will come back to this and use it later. So for now, just imagine that I have a blue edge from this node, which was added when I was 7, to this node, which was also added when I was 7. Okay. Now, this edge is not part of our suffix tree. This is just something that I'm saving to use later in my algorithm. Only the red edges are the edges of the suffix tree. Okay. Now, what is the intuition here? What is the string corresponding to this first node? The string corresponding to the first node is whatever string I get if I start at the root and come to this node. So it's Ana. What is the string corresponding to this node? It's just Na. So actually, this one is a suffix of this one. That's the reason why I'm adding that edge. I will later use this property that whenever I have an edge from one vertex, whenever I have one of these blue edges from one vertex to another vertex, it's going to a suffix. Okay, so the string corresponding to this one, which is Na, is a suffix of this string I have here, which is Ana. Okay, but we have to continue. Again, just like before, after I did this, where is my new location? So you see, let me just copy this. I'm putting it here. So my I is 7. This is where I am, 7. Okay. And so I've added all the suffixes up until index 5. So all of them are done. Now I have to add the suffix at index 6. And how do I know which index is remaining and so on? I will just keep track of this remainder, but I forget to update it. So remember that we have the remainder. We know like how many of the suffixes are already added and how many of them remain. Okay. So my remainder in this case is 2. So I know that what I have to add is this AS, 6 and 7. But what I was adding before was this NAS, right? So this is the NAS that I just added. Okay. What was this NAS that I added? It was basically because of the match here. So it was 3, 4. So it was saying that it's the same as the thing that starts at index 3. So 1, 2, 3. And here, how many steps were I taking? I was taking 2 steps, right? Because I was matching 2 here. So this was my previous location. I had been able to match 2 letters in the suffix that started at index 3, right? So now if I ignore the first letter, which is the letter that appeared at index 5, the N, I just have A. So I have to go to the place that corresponds to the suffix that starts at index 4, but I have to go forward by only 1 step, not 2. So The suffix 4 is here. In this path, if I go forward by only one step, by only one letter, I will end up here. Right? So here. That's my new location.
How do we know the index 2 and 4 are the same letter?
Oh, I know where 4 is in my tree, right? And so when I was adding 4, this thing matched. And because I know where 4 is in my tree, I'm just taking the path from the root to index 4, to the leaf corresponding to index 4. And that path goes from there. That's just what's happening. Okay. Something is wrong here. Am I doing something wrong? No, okay. So now I have S, I go forward, S matches, that's fine. So finally I7 is over. Okay. Now I increase my I to 8, I see an N. What happens now that I see an N? So my location is here, and I'm seeing an N. What should I do? I think I did something wrong at some point, right?
Yeah, we haven't had like the S.
Oh, right. So let me just do this again. Yeah. So I have my remainder. Sorry, I will fix this. So I have 1, 2, 3, 4, 5, 6. Doing this example is always hard. It's much easier to code the algorithm than to do this. Okay. So I've added everything up until 5. So this is my remainder. My remainder is 2. I want to add AS, right? And I have A here. That was my location. I try to match S, and I see that it doesn't match because I have an N. Okay, now that it doesn't match, as usual, I have to again create a new internal node on this edge. So I have to break it into A on one side and NA on the other side. So that's what I was doing wrong. For some reason, I thought that I'm matching with this one, but I was matching in here. This was my location, right? Okay. So now, again, I'm going to take this same graph, and I have to break down this edge. And let me just, okay. So I'm going to have a new internal edge here. And then from that edge, there is an edge to this one. And so this one is the A part. This one is the NA part. And I have read an S. So this is the S part. And now I have another suffix again. And this is the suffix that started at index 6. So this is now AS. Okay. Now finally my remainder is 1 again because I have the AS. Okay. But again, remember that whenever I added new internal nodes in the same step, when I had the same value of I would add these blue edges between them to remember what's going on. So I would also add an edge from the last internal node that I have added to this new internal node here. Okay. Again, these blue edges don't make sense right now, but they will make sense very soon. Okay. My remainder becomes 1. Now I have to basically insert S. And my location is again back at the root. Okay. So I just need to add S, and I'll just add S. So this is just S. And actually what it's saving is 7i. Okay. And here I will have 7. Okay, finally, we are done with I equal to 7. Let's go to I equal to 8. And my remainder is 0 as well because I've added everything. So now my I becomes 8. This is becoming impossibly complicated. So my remainder is now again 1 because I haven't added this last one. Every time I increase my I, my remainder also increases. So now I need to add n. But there is an edge starting from the root, which is my current location, which has an n. Okay, so again, I'm just going to be lazy. What's going to happen is that I'm going to go like this. This is my new location. And also remember that here I had 7i. Because I had 7i, this label is no longer s because I have now increased my I. So this is actually Sn. And this label is also like bananas and this one is also Sn, n, 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 n. Right? Because all of these were just, I had just I there, and now I have increased I. So I was a symbol. It's a different thing. In practice, when I implement this, I put -1 for I. Okay. Great. So I equal to 8 was easy. I go to I equal to 9. So I now want to add this. And remember that everything until 7 is done. So my remainder now is 2. I haven't added my last 2 suffixes. And in this case, I see that I can again just go forward. So I would just have something like this, NA, and then this. But this is basically the same as saying I'm at this vertex, at the next vertex, because I have now traversed all of this edge. Okay, so my location now is actually here. Okay, and okay, this is also fine. I don't have to do anything. I could match. I matched my A. Finally, and the worst part of all of this example, if you can believe it, I read X. Okay. Now, when I read X, when my I becomes 10, my remainder becomes 3 because I haven't added NAX, AX, and X right now. So these are the 3 remaining suffixes that I should add. And I'm here at this point, and I want to add an X. Okay. So adding an X is easy in this case because there is no edge going out whose label starts with X. So I'm just gonna say add an X. What is the label here? It's 8. Again, my labels are always in order, but you could also just calculate it based on the remainder and so on. So it's 8. Okay, so now this means that my remainder becomes 2. So what's remaining to add is AX and X. I have to add these 2 suffixes. But what is my location now? I calculate my location kind of like before, but not exactly, right? So I was at this vertex, right? And what did that correspond to? It corresponds to the suffix that starts at index 8, or the substring that starts at index 8 and goes to 9. So when I was here, I was thinking that I'm actually matching 8, 9, which happens to be the same as 3, 4. Right? Okay, so I was matching 8, 9, and then I added this to match 8, 10. But I know also how many letters I had read. I had read 2 letters because it was 8, 9 that I was matching here. So again, matching 2 letters starting from 8 is like matching 1 letter starting from 9. Okay, so where is 9? There is no 9. Right? Previously, when I wanted to say, okay, I want to match 1 letter starting from 9, I already had it. I already had 9 in one of my leaves. So I know where I have to jump. But in this case, I don't have it. So where should I jump? But yes, exactly. That's the reason I kept the blue edges there. So what is the string that starts at 9? It's basically A, right? I mean, it's just one letter. How can I find A? A is here. Why was that the case? Because whenever I have edges, I said that whenever I have a blue edge, this one is a suffix of this previous one. Right? Whenever I found these suffixes, I added the blue edges. And it's not only a suffix, it's actually a suffix that is just one letter shorter. And that's exactly what I'm looking for. I'm looking for a suffix that is one letter shorter. And I already have it in that blue edge. So my new location is here. I have A, and my new location is there. And okay, let me delete that. And at this point, again, I want to add X. And thankfully, there is no X here, so I can just add an X. And this is 9. Okay. And then the next time I have to actually jump to the root, and I have to just add an X, which is the simple case, which is that I will have just one X here, and this is 10. So now if you forget about the blue edges that I only needed during my algorithm, this is finally my suffix tree. And again, my shapes look awful. So I'm going to show you a better visualization of the same idea. But again, you understand the ideas, right? So the idea is that every time I have a bunch of things that are matched that I'm saving in my remainder because they just matched, but I didn't add them to the suffix tree, right? And as soon as I can add something, I add it. But then the question is, where should I jump in my suffix tree to continue matching? That's the problem, right? But the algorithm actually lets me figure that out based on either what I already have in my suffix tree or these extra edges that I have added. Okay. Here's a better visualization. So bananas na X build suffix tree. So this is my string. It uses $1 for the end string sign. I'm going to start with just having 0, okay? And I'm going to process my letters one by one. So first I process B, which just creates this. So this is my root. I don't know why the root is not on top, it's on the left, but so this is my root, and this is my suffix tree for the string B only. Then I add A. So now, as you see, I have A and BA. It shows you the labels, but again, in the algorithm, we're only saving the intervals. We're saving 2 numbers on each edge. And the numbers that we're saving can be either numbers or they can just be the symbol I. And when it's the symbol I, it automatically gets updated. Okay. So then I add N. As you see, I get AN, BAN. So N was added to the end of these 2, but I also got a new edge. And then I add the next A. So here's the thing. You see the A matches this A here. So how do I show my location? I keep track of my active nodes. So it says node 0, and then which edge, the edge that starts with A. When I want to talk about an edge, I can only say which vertex I am at and what is the first letter of my edge, because the edges that are going out of one vertex have different starting characters, right? And this one is just saying how deep I am in my matching. So I have matched one letter, so I'm here. Okay. In the next step, I read N. Again, you see when I read N, because I is updated, all of these get N at the end of them. But I also matched an N here, so my location went forward. Then I read an A. again, the same thing happens. Now this is that character 7, which was the really painful character S. So when I read S, S is not going to match here. Because S is not going to match, I'm going to create 2 nodes here. And as you see, so this one was Ana on one side and Na on the other side. I'm keeping the Ana. I'm adding the S here. The Na is on the other side. And of course, because I'm adding the S and because the endpoint was I, the S is also added there. Okay. So now, but I have to continue this. I have to continue this. And now I'm here. How did I jump here? Again, the process that we talked about. So I know how many letters I had matched, and I know what was my starting point. So my starting point goes forward by 1. My number of matched letters goes down by 1. So I just end up here. Okay, now I'm here and I want to add an S. Again, the next letter is an N. It's not an S, so it doesn't match. So as you see, I created a new node. But because these 2 internal nodes were created when my value of I, the letter that I was processing, was the same, I added this edge between them as well. This is like the blue edge in my diagram, which is just remembering that these 2 were added in the same iteration. And then the rest of it is pretty much similar. So this is my new location. I'm after A. Again, I want an S, and there is an N here. It doesn't match. So I'm going to add another internal node in here. And every time I add an internal node, if the previous internal node was added when I was processing the same character, when my value of I was the same, I also add an edge so that I remember that this were. Okay. So now finally I'm at the root again. So you can see that my active node is 0. I don't have an active edge. My active length is 0. And my remainder is also 0, which is great. So I can go forward. I can add S itself. Okay. And then finally, I can go to the next letter. So you see, as soon as I go to this letter N, an N gets added to the end of all of these edges. Because the endpoint of all of these edges was I, and now I'm changing my I. Okay. And also this one. Now, this N also matched this N, so I'm here now. That's fine. I read the next character, A, and as you see, it just matched this A. So now I'm at this node. So this was the same as the thing that I told you when I was explaining that when the edge is over, you can imagine that you're just at the endpoint at the node. So this is now my location where I'm doing the matching, and I'm going to read an X, and there is no X. Because there is no X, I'm going to create it. Yeah, so this is the X. Now, to find the next location, I just follow the edge. This helper edge, this blue edge that I had before. So I end up here. I'm at 8. Again, you see that this is what's already been matched. So I continue. I have to add the X. And again, here there is no X. So I add it. I add the X. And finally, I'm again back at the root. I have to add the last suffix, which is X itself. And I add it. Oh, sorry. We also have the $. I forgot about that. Yeah, I thought I'm done. I'm not done. We have to also add the end of string sign, which is the $. But this is pretty easy. So again, when I add the $, my I is going to increase by 1. So you see that the $, gets added to a lot of these implicit labels. But I will also have to add a new node here for the $. Itself. So finally, this is my suffix tree. I will give you a lot of videos with more examples of this as well. The code is actually just 20 lines. So the code is easy. But following why we're doing this, that's the hard part. Okay, and it's actually really easy to prove that this algorithm is correct as well. Like just prove that every step you're jumping to the right place. Okay, so that's fine. But now what is my runtime finally? How much time am I spending? So here's what you have to realize. I'm going over the string only once. So my I is only increasing. So the time I'm spending increasing I is On. Right? What else do I do? I move this pointer, but every time that I move my pointer, either I is changing or I'm adding a new node. So the total number of times that I jump around in my graph in order to create it is bounded by On, because I have On nodes, and every time I'm jumping around, I'm adding a new node, right? So the total runtime is actually On. So finally, this means that using this algorithm, we could create a suffix tree in On. So our pre-processing time is now On, which is optimal. Again, this is the most common optimality argument that you will hear in this course. I have this string S, which is of length N. I have to read it. That's part of my input, right? So that's going to take On time. My pre-processing is also On, so this is optimal within some constant factor, of course, because the O hides the constant factors. Okay, so I do optimal pre-processing, and then I can answer all of these questions also optimally. So if someone gives me a string T, I can answer in all T whether T is a substring of my original string S. And again, this is optimal because I had to read T. I can also answer how many times it appears. I can also answer where it appears. Oh, by the way, when you want to answer things like this, like how many times it appears, you needed to know the size of the subtree. So that's kind of different now, because now I'm creating this tree, but I'm not creating it in the normal way that I was doing with tries. I'm using a different algorithm. So after I create this tree, I just do a bottom-up dynamic programming. I find the size of all the subtrees, like the number of leaves in all the subtrees and so on. That's also On. And after I have that, I can answer those other queries in optimal times. Okay, see you next week.